All right, so today is going to be our third and final study group on neural networks. But before we start, we have some questions about the image data pre-processing, image data generator object here. This is not exactly it, but basically Ali had some questions about the image data generator class as well as data augmentation. So data augmentation is something that we didn't talk about, but is usually something that is used with CNNs, convolutional neural networks, or anything with images. So the idea of image data augmentation, you can sort of think of it like doing SMOTE in a way. Conceptually, kind of the same idea, just kind of create more data. Something that you do with image data augmentation is sometimes you can, just imagine if you have like a bunch of training examples. I think one of the labs go through like, is this photo a photo of Santa Claus or not Santa? That's one of the examples that we had in our lessons. And one way to augment your data. So let's say you can only find, because I don't know, he's a fictional character, you only have 100 images of Santa Claus and a bunch of imposters. If you just want to generate more data, one way you can do that is through data augmentation. And data augmentation, some ways you can do this is, and it's all done in the back end, but you can, for example, like rotate your image a little bit, or you can like tile your image in a specific way, or like flip your image 180 degrees. No, just make it backwards, just so that, your neural network will have more examples of what Santa Claus looks like from your existing example. So that's the whole idea of image augmentation. And that is something that you can add as like a pre-processing step before feeding your data into your neural network. Off the top of my head, I don't remember where exactly in the code or what library you use, but I'm pretty sure there must be something about it in the lessons. Yeah, there's got to be something about it in the lessons, but if not, let me know and I can find some resources. The next thing is this image data generator. So if you have a bunch of images saved on your computer, one really easy way to read in the data is by using, I think this is one of them, using a bunch of, this is basically a step to read in your data. So similar to like, when you're doing pandas.read CSV for your CSVs, you can read in your images in this way. And basically this, I remember it's called flow from directory. Let me just look for that specifically. Keras flow from directory, there we go. So, this is a tutorial. Hopefully they have an example here. All right. So this flow from directory class is basically an easy way to read in your image data from your computer. Because as you know, each image is going to be a separate file. So usually what you'll do is you're gonna have all of your images in some like folder on your computer, and you can, first you have to tell it where it is. With this, some pre-processing steps can be done. So for example, you can scale all your images to a certain number of pixels. So if you know that you don't want to use the full res of your images, and also your images have to be all the same size anyways, just setting a target size for your images, this will scale all your images for you. Also, if you find that your model is taking too long with color data, and if color is not important to you at the moment, you can also have it do grayscale images. It'll actually make your data pre-process much not process, but there will be less information to train on, because in a black and white or grayscale image, there's only one dimension versus an entire tensor of red, green, blue. In this train generator, if you do the batch size, this I believe is the batch size for, let's see, yeah, the number of images to be yielded from the generator per batch. So basically, it's going to read in your images, in this example, 32 images at a time. Not the biggest, I feel like this batch size is not the same as like, the number of images you feed through your neural network. So this is completely separate from that. So yeah, this is just a method to read your data. I don't know, Ali, if you had any more specific questions.
Yeah, if we have time and if it is possible, can we go through image data generator in Keras as well?
Yeah, let me see image data generator from Keras. Let's pull up that documentation. I feel like, is that the one I was looking at? All right. Yeah, so this one is probably the
I guess it's at the end of this documentation. You have.
Oh, okay.
Yeah.
There we go. Ah, here we go. Okay. I see now. So yeah, this is what you use for your data augmentation to just like generate more images for your data set. So for example, I also have not used all of these to be honest, but I know one that you do pretty often is rotation range. So to like rotate your images a little bit, because you know your CNN looks pixel by pixel and it's still like in like squares. By rotating your image a little bit, you can train your image to recognize, let's say like Santa Claus's head is a little tilted in one image. That's something that I'll learn how to, yeah, you can augment your data set by just doing that. Other pretty common ones are, let's see, horizontal and vertical flip. This will just like flip your images right side up or like backwards. I will also say be careful with the ones that rescale your image. So for example, you know how in like Microsoft PowerPoint, when you like adjust, if you have a square image and you like widen it or you lengthen it, your image gets warped. Be careful about that. Sometimes it can help, or it could introduce noise to your data, because you know you can make the argument that if you took Santa Claus's face and you stretched it, you don't want that to be recognized as Santa Claus. You could make that case, but it's really dependent on your context. So things that would affect that would be, let's see, where is that? This one, width shift and height shift range. So as you can see, hopefully it says here, yeah, so basically the fraction of, yeah, so basically how much it will change the width and height of your image. So yeah, all of these, I would say I've not used all of these, to be honest, but yeah, the most common ones you would want to do are the ones that just rotate your image or flip your image, just to have, you know, more examples of images for your neural network.
Because I want to use this for CNN, it's not very useful to flip an image, for example, because in CNN we feed in the matrix instead of vector, right?
Well, kind of, I would say it also depends on the structure of your convolutional layers, right? So if you flip an image, you might have, I don't know, you might miss certain patterns if you don't have an image flipped. I guess you could say that, I guess, yeah, in the backpropagation process, you could have a filter that does the flipping for you. But also it's hard to say if it ends up doing that or not. So yeah, therefore flipping is, it's actually, yeah, it is done. But I mean, yeah, you can, I guess you could also make the argument that not. If you want to do fewer epochs, I would flip the images. If you know you're going to run your model for a long time and do like over 100 epochs, then sure, you can make the argument that you don't have to flip your images.
Okay, thank you.
You're welcome. Anything else on images before we get into today's material? All right then. So for today, couple things I'm going to talk about. We're going to talk about pre-trained networks, basically using weights that have already been trained, so that it speeds up your training. And these, yeah, I'll talk about this when we get there. Next, doing grid search, or I'll introduce this library called Telus that I personally like a lot to find optimal parameter combinations. Telus is basically grid search, but it was created for working with Keras. Next, fairly simple, but it's surprisingly a question that I get a lot: saving your neural network to disk, so that, if I have a neural network in this notebook and I just want to reuse it in another notebook, I wouldn't have to retrain it all over again. So we'll talk about that. And then I actually have a slideshow on recurrent neural networks that we're going to go through. So to start, let's talk about pre-trained networks. So a pre-trained network, or for CNNs, it's known as a convolutional base, consists of layers that have already been trained on typically very general data. So for images specifically, these layers have already learned general patterns or textures or colors, such that when you feed in your training data, certain features can immediately be detected. So for example, most of these pre-trained networks have been trained on this like image database called ImageNet. And so a lot of their nodes would already be specialized to detect certain things. So for example, maybe combinations of colors, perhaps, you know, they recognize specific like textures. I know ImageNet has a lot of like animal pictures. So maybe there are some nodes that have already been specialized on detecting, all right, is there fur or are there like scales, for example? Again, we don't know what these are. So yeah, these features can immediately be detected. And then this part is known as feature extraction. I actually have an example, so we'll talk about what's going on there. So after you've done this feature extraction, like, you know, having your neural network pre-trained layers already detect these specific things so that your own neural network won't have to do that work, you can typically add your own final layers to train the network for your purpose to classify or regress based on your problem. So this component is known as fine-tuning. There are a lot of pre-trained models that already exist within Keras, and I'll actually show an example using one called VGG19. But yeah, you can take a look at all these models. I know there are dense layers. There are, so these I know are convolutional layers, but if you know that you want to use some sort of pre-trained layers, feel free to do this. The idea of using a pre-trained layer is very, very similar to using word embeddings that were built by GenSim or Spacey and NLP. So you're just using something that has been trained on other things. Questions about that concept?
Can we use that in our project?
Oh, absolutely, absolutely, yeah. I actually won't run it because I know it'll take a while, but I'll show how you could set up a pre-trained network. So I'm not going to run this notebook because it takes a while. But here you can see I have my Keras stuff. I'm going to import, well, the sequential model as well as dense layers, but everything else I can get from VGG19. So very, very straightforward. All you have to do is import the pre-trained network that you want to use. And then usually you want it to already have weights. So the weights usually come from ImageNet. ImageNet is basically what it was trained on. Just to show, include top equals to true versus, and I have another example here of include top equals to false. It, again, depends on what you want to do. Input shape, it will depend on the shape of your data. So if we take a look at this pre-trained network, one thing that you can do is look at the summary. And this summary is actually pretty neat. It'll show you every single layer in the pre-trained network. So as you can see here, there's a bunch of layers, a lot of convolutional layers, some pooling layers, more convolutional layers. And then at the very end, it flattens, and then you have your dense layer that creates predictions at the very end. So this layer is already pre-trained to make some classification based on ImageNet. Typically, we don't need this last layer because we don't even know what this is predicting. So based on this, what we can do is we can take this pre-trained model and use most of it. So most of these layers, and as you can see here, the number of parameters in each layer, and this is actually pretty wild. Like for example, in this layer, we already have 37,000 parameters. Here we have like 147,000 parameters. And these are all the weights that are being changed. So actually, if you sum it all together, the total number of parameters here are 143 million. So you can imagine how much training needs to go into optimizing 143 parameters all at once. So usually what we do is we don't include top. And if we don't include top, we don't have this final prediction layer. Some people like to take away more layers. So for example, I don't know if I did this here, but okay, yeah. So for example, like this flattening layer is when you go from detecting patterns to beginning to make like your predictions. So here, if I do include top equals to false and take a look at the summary now, it ends at a max pooling level. Then you can add your own flattened level and your own dense layers that are untrained. And then so all your model has to do is to update the weights of only the last couple of layers. So as an example, if I instantiate a CNN model here and I add my pre-trained network, so by just doing this, I'm adding all of these layers, and this is the second one. So all of these layers into my model. Next, what you have to do is you freeze your layers so they don't get retrained, because you don't have to retrain them. So basically each layer, and this is sort of the same as like, I guess it's an attribute. Whether a layer is trainable or not is an attribute, and by default it is set to true. So what you can do here for layer in CNN.layers, you can set it to be false. So therefore, when you compile your model and fit your model, it's not going to update the weights in these layers. And I mean, if you set it to trainable equals to true, it will have some initial weights, but they will still be adjusted. So your entire back propagation process is going to take far longer, which is something you can do as well, but typically people don't do that. So after we have these layers, I'm just going to add a couple of my own layers. So here I'm doing the usual flatten layer, just one quick dense layer. Typically you have a couple more. And then I have my final layer with a softmax activation. Softmax here, I haven't even set up, there's no data. I'm not going to run any data through this, but if it's multi-class, you'll have softmax, and if it is binary, you have your sigmoid function. So here you can see I'm verifying that the weights for my pre-trained layers are frozen. So here I'm just doing for layer in CNN layers, print the name and whether it is trainable or not. So you can see because we set these to be false, everything in VGG19 is false, and then all of my own layers are true. So right after this step, you can compile and fit your model, and it will be able to more quickly detect patterns. I think this is all I have, yeah, for this part. Any questions about this? Cool. If you are thinking of using a pre-trained model, it might be worthwhile to take a look at the pre-trained model documentation just to see what it was trained on. If you want to make a decision on what pre-trained model to use. I believe in the lessons they used one called ConceptNet. Off the top of my head, I forget what the difference is between ConceptNet and VGG are. I believe they are trained on like similar information, but based on what your question is or what you're trying to classify or predict, one might make more sense to you. Something else that you can tune, you can also try a project with different pre-trained models to see which one performs best. That's also something that you can choose to do. But yeah, before we move on, any other questions on pre-trained networks?
I have a question about pooling layers.
Mm-hmm.
Why we are using them?
Mm-hmm. So the pooling layers are sort of like detecting what are the more important features within a convolution. Why they decide to do that, to be honest, I'm not sure what the why. I'm not sure why that is a thing that I want to do, but the idea of a pooling layer is you can extract the most salient information. It kind of comes, as you can see here, I've talked about like this funnel structure. So you can see that as we go down, the output shape keeps decreasing. So that could, I don't know, the pooling helps to decrease your, the dimensions of each image, if that makes sense. Why exactly that's the case, I'm assuming it's to try and detect things that are more important than others. But on like a theory level, I don't think I can answer that with confidence. So yeah, anything else?
Are there any kind of pooling instead of max?
Oh, yes, there is average pooling as well. It's usually between max pooling or average pooling are the ones that I've seen used most. So max pooling, if you remember, wait here, I think I have the notebook from last time somewhere in all of my tabs. Let's see. So yesterday we saw that pooling layers here. Once you have this pooling layer basically takes the biggest number from each 2 by 2 square. The average pooling will take the average. Anything else at this point? All right. Next, we'll talk about doing grid search with Keras. So there's a couple ways to do this. One, you can actually use grid search. All you have to do is you have to kind of coerce your model, coerce your neural network into something that scikit-learn will be able to recognize. I personally haven't done this. I actually use this other one, but feel free to take a look if you don't want to like learn another library. All you have to do is, where's the step that I want to show you all? Here, you want to turn it into a Keras classifier so that it can be used by scikit-learn. And then you have your hyperparameter space, and this part is all the same. You can use all of GridSearch's built-in attributes and methods. So feel free to use this if you'd like. Things that you can tune. Here you can see they're tuning the number of epochs, the number of batches, and the different kind of optimizers. You can also edit like things like the number of units or what activation function to use. If you do a quick Google, I did a Google before this, and you can actually find other examples. So there's that. The method that I like is using this other library called Telus, and I'm just gonna walk through a really quick example. I like Telus for a couple of reasons. It lets you tune without having to create that model object for scikit-learn. But also what I like is it automatically outputs your parameter combination scores into a CSV file. So I'll walk through this whole process, but let me just show you the output. This is a file that was created automatically. So I was tuning a bunch of different things, like I was tuning my activation functions, I was tuning like how much to drop out, different optimizers. And for every combination of parameters, it showed me the scores. So let's say I don't like the best one, I can pick my parameters afterwards. So that's why I like Telus. It is a little bit harder to learn. I have linked a couple walkthroughs. So, well, I guess just this one, but it's pretty straightforward. And their documentation is actually pretty nice too. So just to show a quick example of how to use Telus, this is going to be the same data set that we use on Tuesday. So it's not going to be images just because this is a smaller data set and it'll run faster. But I'm just going to import Telus like this. I have my usuals. I'm even using train test split here. So we know all of this. The one thing, instead of having your model as like this model object, I'm just creating a function that builds my network for me. And so Telus actually requires your network to look like this. It also works with convolutional neural networks, just in case anyone was curious. And also recurrent neural networks, if you want to do that. I've actually done this with a CNN for my image classification project. So these are the inputs that have to go into your function. It has to be this way. But then other than that, you just build out your model. The next thing you have to set up is think about what do you want to tune. And for each thing that you want to tune, you just create something that calls on your parameter dictionary. So just in the same way as grid search, I have this parameter dictionary, but the plus is I can call these whatever I want. So basically, for example, let's say with this one, I have this dropout layer, but I'm not sure how much dropout I want to do. Here, I'm going to test dropout with 0.1, 0.3, and 0.5. I can call this dropout. I can even call it dropout 1, dropout 2 if I have more dropout layers. But basically, I just save this as params dropout. Your values that you want to test have to be in a list. And you can do this for anything that can be tuned within your neural network. If I want to change the number of nodes, I can do params and call it, for example, nodes 1. And then let's say I want to test the number of nodes. Oh, I don't like that formatting. Let's just do it here. I will do nodes 1 and then come up with a list of the number of nodes I want to try. Maybe like 20, maybe I want to try 100. So that's how you go about setting it up. You do have to output your model, your history. Basically, we've been doing this so that we can print out our history. And also you have to return the actual model. After this, what's pretty cool is within Telus, you just have to use their scan method. This is in values just because they need it as an array. So I'm just putting this as .values, feed it my parameter dictionary, feed it my model. And the model comes from this function. And then just as an experiment name, this is just the name of the file that is going to be output. So I'll show you what that looks like too. And then after you do this, this is a progress bar that will show you how many iterations of modeling it's doing. So here, well, before I added this, I had 24 different combinations of parameters. It'll show you how long it takes all of them. It actually gives you like, this took 24 minutes, I think, for me. No, that's not right. This took 24 seconds because it's, yeah, not convolutional. But then also based on what metrics you have here, you can actually pick your best model based on whatever metric it is. And you can actually use this model to make predictions. However, what I find more helpful is to just read out this CSV. So with this grid, and actually let me pull up my home page real quick so you can see what that looks like. I have a lot of stuff here, but this was created automatically after I ran the scan function. And then here, this is the CSV that I read into the notebook. What is awesome about this is that this CSV is updated with every iteration. So let's say it runs like 5 iterations and I don't know, your computer full memory, you'll have those first 5. So that's pretty helpful to have. So you don't have to rerun the 5 again when you rerun your grid search. So on top of that, within this, you can also have it randomly select a subset. So it won't run all 24. Maybe you only want to do like 20. You can do 0.8 so that it'll 0.8. No, that's not right. 0.83. So that it will run only, not every parameter if you don't want it to, it's like randomized grid search. So yeah, this will work for any Keras neural network. It doesn't matter what kind of layers you have. This is how you can test different combinations of anything that you can tune. So yeah, any questions about this?
I can see in some data set, they divide their data to test, validation, and train.
Mm-hmm.
What's the difference between test and validation?
Yeah, I always forget which order is which. But sometimes because, especially with Keras and TensorFlow as well, because when you fit the model, it validates your data in the fit step. So it is training your model to try and optimize this data. So sometimes it can be overfitted to that specifically. This part is not necessary, but if you want like another step of validation, because you know there is a tendency to overfit to whatever this subset is, you can have a third subset of data. So you call it train, test, and validation set. I forget. I guess it makes sense that this is the validation set and your test set is after you finish running your model, you do one more layer of testing to make sure it's not overfit. So yeah, that's where you would use like your 3 subsets of data. Because if you imagine like doing cross-validation on a neural network is going to be extremely, extremely intensive. Any other questions about doing grid search with neural networks?
Realistically, how long will that take to do this grid search?
Yeah, I will tell you that I remember my project on image classification, I ran a grid search for like 6 hours. And I didn't even search, I searched through less than not more than 50 combinations. And that took, well, again, it also depends on what your image size is. That's also something that I had to play around with like decreasing my image size so it didn't take too long. So yeah, I mean, you can sort of get a sense as to how long it will take by running your model once before you do a grid search. And then if you just use that as like a base and just multiply that time out. So yeah, it does take a while because it is building and testing that many combinations of parameters. So yeah, it can take a very long time. Remember that this is a very, very small data set, which is why it only took 24 seconds. It only took 1 second per iteration. But yeah, you can imagine if with images, this only has 8 columns. Images, you would have hundreds, thousands potentially. Yeah, probably closer to thousands. So yeah, it will take a long time.
Could you do a smaller data set, or is that probably not good practice?
You could. There is still there is usually what's the benchmark? Yeah, usually you want to have about 1,000 occurrences per class. I would say one of the quicker ways to speed up your neural network is just decrease the image size. So in like earlier, we were talking about your pre-processing. Here, your image size, you can decrease that, but you lose a lot of detail, right? Imagine if you have like a very pixelated image, it'll be harder to pick out specific patterns. And you lose a lot of like texture information once you do that. So it's like, yeah, you weigh how much time you have. I will say most students who do like grid search on like a CNN project, they end up running models overnight. And having something like Telus that will output your metrics for each combination makes it easier. Just in case it breaks, you don't have to restart everything from scratch. Anything else? Cool. Now, next part's gonna be really quick. Just want to talk about saving your model. So this is the model that is built with all the best parameters. Oh, and as you can see, ReLU just happened to outperform hyperbolic tangent, and Atom, for the most part, tended to outperform SGD as an optimizer. But anyways, this is just the neural network with all of these best parameters. This part I won't go through too much. I added a bunch of epochs to see that our accuracy ended up at around, let's see. So this was an accuracy of about 68%. So let's say you had this model, very, very painstaking process of training this model. We don't want to do this again. Oh, graphs just to show, but you can save your model. So saving your model is just a matter of doing model.save. Something that you also want to save is the weights of your model. So you do have to do these separately. This part just saves the layers. This part saves the weights and the biases within your model. So typically you would do this in a separate notebook if you just want to have your model to work in somewhere else. It could be even in a script, in a Python file. You can just load up your model, and this is using the same file, and then load the weights into the model. And I ran this before the study group, but you can see it has the same accuracy as the final epoch. So 0.6811, 0.6811. So we know that it's the same model that has already been trained over all of these. Questions about saving your model? Cool. Finally, I do want to talk about recurrent neural networks. There isn't much material on recurrent neural networks, but it is a pretty neat extension to time series, to NLP. So I do think it is worth trying out if you're interested in going that direction. Again, I do want to reiterate that at first jobs, it is not likely that you will be using neural networks, but could be cool to have in a project. These are all examples walking through neural network projects. So you can see like the code that people are using. All in all, it's just a different kind of layer. The same way that yesterday we talked about convolutional layers and pooling layers, it's just different layers. So these show walkthroughs, and I do want to get into a PowerPoint presentation about RNNs. So really, really quickly, let's just present this. There we go. So recurrent neural networks. We're going to speed through this a little bit in the interest of time. This was for the in-person course as well. So I'm not going to go into everything in a lot of detail, but there's a bunch of resources linked at the end of this, and you all have a PDF version that you can go to those resources. So one thing to think about when you're thinking about, all right, do I want to incorporate an RNN, is when you have sequence learning. So sequence learning, you're not dealing with just a collection of items, but also an order matters. So with things like time series are like very, very direct usages of RNN. The other thing that a lot of people in this program use RNNs for is for text generation or text prediction, like predictive text. Like, you know, if I think of like, I don't know, on your phones when you have like the predictive text for the next word, things like that. So for example, ABC will produce a different outcome from ACB. So several considerations: how can each element be represented numerically or as a vector? And sequence length, is it going to be variable or constant? And by sequence length, I mean by, all right, if I want to make predictions, am I going to predict 1 word at a time, 3 words at a time? Same with time series forecasting. Am I going to predict for the next week, for the next month? Sometimes it matters, sometimes it doesn't. So just an example of some examples of sequence learning. Frequent pattern mining. Pattern mining is actually a whole nother field of data wrangling where you're trying to pick out common patterns. A really, really simple or relevant example of frequent pattern mining is looking at n-grams in text. So if you see, you know, groups of 3 words that appear a lot together in your text, that's a frequent pattern. ARIMA and all of its variants, those are also examples of sequence learning because it's trying to learn sequences. Markov models that we didn't talk about, but I believe is in the appendix of phase 2 because it is probability based. And finally, sliding window models. And sliding window models are what we talked about with generating word embeddings. So you're training a word embedding for a specific word based on the words that commonly occur before and after it. Questions about any of this so far? All right, so why isn't a regular multi-layer perceptron enough? So as a simple example, let's say we have univariate time series. Now univariate time series, let's just say we're using past stock prices to predict the price of a stock tomorrow. Why is a multi-layer perceptron not enough? If I were to feed in the inputs of, you know, the 10 days before to predict, you know, today, that might not be enough because you're not treating each input as a sequence, you know. Regular multi-layer perceptrons, and also, you know, if you think about the earlier example where we had that Pima Indians data set, or even with like pixels, it doesn't really take into account the order of your inputs because it's just going to be fed through each and every node and it's going to readjust weights, but has no regard for, you know, this is yesterday, this is the day before, this was 3 days ago. So we have recurrent neural networks. And just as a comparison, this is a regular forward feed neural network, and this is a recurrent neural network. The only thing that's added is really this like arrow that brings it back. So regular forward feed neural networks have an activation function that is fed all the inputs and then just goes to the output. RNNs use a recurrent activation that is also forward propagated and is fed from the output of the previous step in the sequence. So what an RNN is doing is, just imagine if I have a neural network that's trained, it sees, all right, tomorrow I'm making this prediction that the stock price is going to be $100. It also takes into account that, all right, $100, I find out that the actual price was like $95. I'm going to take that into account when I'm making my next prediction. So it is going to keep on one hand, it takes in your inputs as a sequence, but 2, it continuously updates with new data. And that's the whole idea of like the recurrence. A couple things like not adjacent to this that isn't in this presentation is that usually the activation function used for RNNs is hyperbolic tangent. To be honest, I'm not sure why either, but in a bunch of the walkthroughs that I have linked, they show that the activation function is hyperbolic tangent. But yeah, any questions at this point? Okay. So there are many different kinds of recurrent neural networks. If you get into the weeds of learning how RNNs work, and I will admit that I feel like I'm not there yet. RNNs are actually represented slightly differently because you have time as a component. So, you know, we're used to seeing that like web diagram of a neural network like this, but recurrent neural networks are actually presented in this format. So at the bottom, you actually have your inputs. These are your recurrent neural network layers, and then these are your outputs. So these are just a bunch of examples of different kinds of structures. So, you know, you have, let's say, just one input to predict the next thing. Sometimes you have one input and you want to predict multiple things. If you have multivariate time series, for example. These are other examples. In the case of like text prediction, if you want to predict just the next word, you're going to feed it in, you know, the 3 preceding words to get to your next word, and so on and so forth. I'm not too sure of other examples of this. I think if you want to like generate like one example that you can use is in generating, for example, Spotify playlists. If you want a Spotify playlist, one way of doing it is by feeding it in examples of other playlists, and it can actually give you additional things. There have been a couple RNN recommendation systems that I think are really interesting, but I haven't really gotten into the weeds of those. But if anyone's interested in that, I can send out resources for that. But I don't want to spend too much time on just these pictures. Some really quick RNN examples. As I mentioned before, in NLP, predictive text and sentiment analysis are some uses of RNN. In sentiment analysis, it is trained using some RNNs. Some recommendation systems. There have been examples of recommendation systems I've mentioned using RNNs. Also multivariate time series forecasting. And that is, for example, you want to predict the price of multiple things at once. And then, yeah, all of these other things, audio interpretation, image recognition, and recurrent convolutional neural networks for videos, which is pretty cool. Very, very advanced, though I have not done that before, but it does use RNNs. Any questions at this point? All right. So this part I'm not going to talk about because it's way too much math. I'm going to get into here. So with RNNs, the next most common thing, and we're going to talk about, is LSTMs. So LSTMs are a subset of RNNs. LSTMs basically have this idea of, LSTM stands for long short-term memory, and it basically is an RNN, but also includes what is important in the past and what is not important in the past. So as a really quick example, in this predictive text, there was a castle in the mountains on a river across from the valley where the king's army was marching. So things that are very, very obvious. Kings is obviously related to army. Army is obviously related to marching, just based on the words being close together. One thing that is less obvious is the connection between the word castle and the word king. So the word king and castle should be an obvious connection, but it's too separated by other words, and the model has forgotten. And so the way that LSTMs work is they try and figure out what is important to remember over longer periods of time, and what are words that are maybe less important. Does that make sense? So that's why it's long, short-term memory, because things like castle, they will probably see as, all right, I got to remember this word castle. All these other like stop words, like in the, maybe like across, are less important, so we're not going to remember those as much. So when we get to king, we'll be able to say, all right, if I want to predict, let's say I have the sentence all the way to here. There is a castle in the mountain on the river across from the valley where if I want to predict the next word, with the context of castle, king could be a more probable next word. Questions about this?
In auto-completion, in social media, they use these?
I think so. I'm not 100% sure. I mean, they probably use some variant of an LSTM. Based on all of the technologies I know, there might be something way more advanced out there that I'm unaware of, but it makes sense that they use LSTMs, yeah.
Yeah, I've seen projects using both transformers and LSTM for like sentence completion.
Mm-hmm. Yeah. Anything else? Cool. This is what the structure of an LSTM looks like. The new thing that we're going to, that is part of an LSTM is this forget gate. I guess for now, this part would not make sense, but don't worry about it for now. But this addition of a forget gate is how it determines what information to keep and what to throw away. Yeah, the rest of the stuff is kind of similar to what we had in our previous kinds of layers, but yeah, the long short-term memory part is basically what this forget gate deals with. Cool. Well, that was a really, really brief overview of RNNs. It's not really part of the curriculum. I personally haven't had too much experience with RNNs or LSTMs, but here are a bunch of resources. Further applications, I know that in the appendix, they do talk about gated recurrent units, so GRUs. There are also bidirectional RNNs that basically learn back and forth. I have not even gone into looking at those yet. But yeah, this is a bunch of resources. Again, this is the famed Coursera course on deep learning. A lot of people do say that that course is what helps them fully understand deep learning. I will say I did take a look at these resources. This one is pretty cool. It's a YouTube channel where this guy basically builds projects over different YouTube videos, and he has a series on deep learning, and this is the video that he built in RNN. And yeah, feel free to check out all these other resources. They're all related to RNNs and LSTMs. But yeah, that is all I had to talk about today. Are there any questions at this point? Cool. Well, that is all the curriculum that we have, which is crazy. Tomorrow, I'll be doing like a brief overview of each of the 4 projects. I will be getting your project pairs out by today. I just need to wait for a couple more people, some of who are on this call, to let me know what their project is, so that I can do those pairs as soon as possible. Yeah, I mean, something that I also wanted to talk about is that very, very common, people feel that at this point, they haven't learned anything, which is very normal. In my experience, I felt the same way too. Like you guys are constantly taking in new information every day, and it really hasn't gotten the opportunity to sink in. Maybe some a little bit during the project weeks, but totally understandable that it's flown by so quickly, and the information just has not sunk in yet. I will say it does get better, especially over the capstone project, because you have time to sit with what you've learned, and also in the months following graduation. So I just wanted to address that common concern, not just in this cohort, but other cohorts as well. It's very, very normal to feel that way. If anyone wants to talk about it, I'm happy to talk about it too. So yeah, that is all curriculum. Over the capstone period, we're still going to have these study groups Tuesday through Friday. So I will be occasionally talking about, one, it's going to be a bunch of review stuff, because I know, for example, for this capstone project, you're going to have to do APIs and web scraping. So I'm going to review those. I'm sure it's been a while, as well as some of a little bit more informal study groups on, further applications of the things that we've talked about throughout the course. Yeah, but capstones comes later. First, we have our phase 4 project coming up. So tomorrow I'll be doing that overview and intro. If you take a look at the calendar, I've already set aside the first 2 days of our capstone week to be project presentations. So yeah. Cool. Any final questions before we close out?
Yes, I want to remind you that I asked a question yesterday. Yeah.
Yes. Oh my gosh. I'm so sorry. I keep forgetting. I literally have it written down right here and I keep forgetting. Anyways, Ali asked about how does object detection work? Object detection is actually really, really neat. You can sort of think of it as like a pre-trained network. But basically, object detection works after a lot of training. Basically, you're training a bunch of classification algorithms to learn what objects look like. So if you look at object detection libraries, there is a limit to the kinds of objects that they will be able to detect. So it's basically a bunch of classification models put together. And then it's also probabilistic. So one thing that, if you build your image classification model, one thing that you can do is you can actually display a heat map of where in an image is causing your classification. So for example, if you're doing like a tumor detection, you can actually create a heat map and very likely it will show like red over the tumor. So something like that, like mapping a probability of your object classification onto like an image or a video, that's how you do object detection. And then another thing that you do after that is you can also pick out exactly where the object is in an image based on this probabilistic map. You guys will not be training your own object detection models. But there are libraries that are already built out for that. So there are ones for like very general objects. The most popular one, I believe, is called YOLO, stands for you only look once. And also there's a couple face detection algorithms as well, libraries as well. So you just have to install the library and it'll be able to like show, like zoom into like where the faces are in an image. But yeah. That's super quick overview on object detection. You likely will not be building your own object detection models. Thanks for reminding me, Ali. Anything else? Cool. Well, yeah, it's crazy. It's the end of the curriculum. There will be more coming, but in like smaller doses over the capstone weeks. But for now, let's focus on our phase 4 projects. Please, the people who haven't yet on this call, I see you. Let me know what project you want to do. In the next hour, I will be slacking. I'll be poking you more if you don't tell me. So yeah. All right then. Have a good rest of your day, everybody. I'll see you all tomorrow as we kick off the phase 4 projects. Bye.
Thank you.
Bye.